Right, well, just give me the camera a chance to settle. So what I did last night was I tweaked all of the rotors to optimize the output on the current and the voltage. By doing that, it obviously improves the output waveform, which is a lot better, it's more stable. However, we have lost a little bit of RPM, so that is what we're getting right now when it's still picking up speed. We're at about 61 Hertz, and peak to peak is 19.4 volts. Cyclic RMS voltage is 5.92 volts. It's almost at 6 volts now. And the waveform is much cleaner. However, we're still running through one choke on the LED. You can't really see it with the light properly because I stand in the shadow. So you can see the LEDs are nice and bright, and the LEDs are currently consuming through one choke where the LEDs are getting 7.3 milliamps. Our speed is at 1244, but it's still climbing. It's definitely much better, but let's check the input current. Input current is actually bang on the nose with 200 milliamps, and we're still running it at 6.5 volts DC. That's what drive for the drive motor. I'll check the voltage. Should be 6.5 volts. Yeah, what, 6.6? It's near enough. Right, so I thought I'd show you what I did, because I wanted to optimize. There's no point doing this if we don't get a decent amount of current and voltage coming out. I have had some thoughts I'll share in a minute. Obviously I got it really well balanced. I can barely feel any vibration on this thing at all now. It's very stable. I don't know how I can show you that. Let's get a ball bearing. Right, so I got a ball bearing here, and if I stick the ball bearing on here, without it rolling off, well, you can see it's on a slight hill. It's very stable. If I put the ball bearing there, it's going to be influenced by the magnetic field on the rotors. Well, look at that. There you go. You can see how little vibration this thing has. You see, if it was vibrating really badly, I wouldn't have been able to get that ball bearing to sit there at all. But the field is influencing it, the magnetic field is moving it a bit. So you can see it's very quiet. I'm happy with that. The output current to the LEDs is currently 7.3 milliamps. Let's go through two chokes. Let's watch the LEDs. That's through two chokes, and the current consumption is 40.5 milliamps. That's a bit too high for them LEDs actually, but yeah. And we're losing RPM a little bit, but not much. So now I have been thinking, I don't want to blow these LEDs up. I have been thinking about driving, because obviously at the moment I'm using this tiny little motor down here, right, which is what's consuming the power from the input. I have been thinking about possibly using my other generator project which I built previously, which has pulse drive on it. It has a pulse drive system. in the drive bay down at the bottom. I think I showed you that. Well, you can go look at early videos, but it's got a pulse drive coil network underneath, and it's got timing, adjustable timing, which the start and stop times using trigger coils. I have thought about using this just as a motor to drive that thing, you know, using belts, using a drive belt from here, from the pulley hit on here, and linking it to the pulley on the other one. But then there's a problem: I don't have a belt big enough. Unless I put it back to back, I could put it so that the belt, this point is facing towards that part. Maybe I have considered it. It'd be interesting to do that probably in the distant future. I don't want to do it right now because it's just a lot of fighting about, and it's such a mess. I have to think about it, but because this system, you can control the timing on it and optimize the current input and minimize how much power loss there is. But obviously I'm not going to be using the output coils, which are these things. These output coils not used right now, but I could use the drive part of it, the pulse drive system, because the reason why I was thinking about that is because I could maybe get the input current even lower if I was driving this thing directly using that. Because this thing's capable, this particular unit is capable of going up to 8,000 RPM, right? It's capable of going really, really fast, right? Whereas that one, I don't want to go much above 1,500 RPM, really. We're at 1,200 right now. So I thought about doing that just to do an input current comparison. Yeah, I'm not feeling up to doing that right now because there's a lot of fighting about. I need to clear my table anyway. I've got to clear all this junk and just basically thin things out a bit. But it would be interesting to see what it could do. Obviously this uses a higher voltage on the input, which is stepped down to a low. I use that unit there to drive the pulse system, and these are the timing pulse drive board down there, which is what sends the pulse to the MOSFET driver, which is down here. It's covered in dust right now. That's how long it's been sat there. And this has come away from the heatsink. This MOSFET down here has come away from this heatsink, so I'd have to stick that back down somehow. Yeah, otherwise it might overheat. I don't know, but anyway, it's just some thoughts I was having last night. Now, the other thing I was thinking about was the when I was designing this thing, when we're using these anti-drag magnets on the outside perimeter of the segments. If we had stronger arrays, right, if these magnets that are on the perimeter here around in these slots, if these magnets are a lot stronger, right, we should be able to get an even better response on the anti-drag system, right? Because the magnets that are in the middle that are driving the coil to produce the output power and voltage and current, they're set back a little bit. It's relative, so the greater the amount of power that you send into the coil is equal to the amount of anti-drag feedback that we get against these magnets, because the amount of power that's going through the coil is what's reflected back to the anti-drag magnets, right? So the weaker the input current is, or input power is, the less we have on the anti-drag system. That's why last night I reconfigured the magnets on the rotors, because I realized by reducing the actual field, by using fewer magnets in these slots down here, it wasn't going to benefit me much, because it would induce a weaker reflective field coming back on these anti-drag arrays. So it was shooting myself in the foot really by thinking that by reducing the amount of field strength it would benefit me, because it doesn't actually do that at all. It's yeah, it's less efficient. So what I did was I boosted the field strength by optimizing these magnets on each side of the magnet to reflect, to concentrate the field stronger, so that we have a bigger bubble. And it's a much stronger field coming around here now, out of here and out of there. So because that field is much stronger, we see a bigger anti-drag system, but it only seems to work in effect when you have it loaded down. But when I load it down, we do lose some RPM, which is to be expected, because there will be a certain amount of offset. There's a compensationary part of it that I don't know how to explain it really, but it's like if you've got a pie, right, and you say, I don't want to cut my pie, right, then if you don't cut the pie, then the pie is going to maintain its full size. But if you say, right, I need to cut the pie, am I going to cut a small piece out of the pie, or am I going to cut a large piece out of the pie? Well, it's proportional. So if you cut a small piece out of the pie, you'll lose less RPM, right? You might say lose 50 RPM or 20 RPM or something. But if you take two pieces out of the pie, you might lose 70 RPM, right? You won't lose double, you won't lose 50 plus 50, you might lose 70. But if you take three pieces out of the pie, you might lose 100 RPM. You get what I'm trying to say, right? It's and if you basically cut the whole pie, if you eat all of the pie, half of the pie, right, instead of losing everything, right, like say, well, let's say we're running at 1200 RPM. Instead of losing 100 RPM or 200 RPM, you might lose 150 RPM. So it's, and also as this thing slows down, the output is lower as well. So you have an offset. It tends to balance itself out. It's really hard to explain this. It's really, it's like a logarithmic. If you know what logarithmic and linear scales are, if you don't go and look into what logarithmic scales and linear scales, you'll be able to get an idea what I'm talking about. So this is basically logarithmic, right? So you might have a small change at the top end, and it might not be a large change until you get to the bottom end, right? Anyway, I think I'm rambling, to be honest with you. So anyway, there's the outputs at the moment on the oscilloscope. Let's settle down a bit. Look at that, we've got cyclic RMS of 6 volt right now. Our input current's dropped to a fraction of 190 milliamps. We're still at 6.5 volts, so we're just a tad over 190 milliamps. So we're actually improving things. I mean, based on the output and the fact that our LEDs are using more current as well at the moment. We're using 7.3 milliamps at the moment. I'll save my batteries actually. And our speed is picked up to 1276. Anyway, that's an update on where we are right now. As obviously I've got to do some more thinking. I've got to wind some more coils. Now that's something else I wanted to tell you about, is coil optimization. Winding the coils in an optimum arrangement will also improve the situation where we have less drag, right? If I wind the coils properly, we should be able to have even less drag on the system, because the coil width, how wide the coils are wound, and how they're actually arranged on the canopy, that can make a hell of a difference on its efficiency and how much drag we see on the system. So these two coils at the moment over here, these two probing coils, they're shorted out right now. I've got them shorted together by bringing, I haven't got them hooked up to the meter, but just by bringing them close to the rotor, we should see how much RPM we lose on the RPM meter when I bring them in. So if I just bring these in, you can see how little effect they have. So I'm just bringing them in, and this should short it out. I don't know what the current is right now because I've got the meter hooked up to them, obviously. But when we did previous tests, we had over 194 milliamps when I brought these in. It'll be a hell of a lot more than that right now, because the output on, as you know, the voltage on the oscilloscope is a lot higher right now, and the field is a lot stronger on this rotor right now. So we can guarantee that when I bring these two coils in, we're drawing more than 100 milliamps out of there, just by bringing them into the close to the rotor like this. Right. Let's look at the RPM. See that? It's barely dropping. So there's definitely some work to do with the coil. I might even wind some coils that are in a long like this, but vertical, so they're sticking up like these. I might actually put some 3D print something too, so I can wind the coils vertically on the back of these canopies to do an experiment. Instead of having these like this, instead of having the coils wrapped around like that, I might try winding some coils in one single place, like in that area, to try an experiment to see how that does. It will be interesting to try that out. That's probably another step to do. So we could improve, we could actually get quite a considerable amount of power out of this thing without actually putting a huge massive load or on the system, right? So anyway, there's a lot of things we can try out, and I'm going to go and watch vintagemachinery.org right now. I've got it on pause right now and watch. It's doing a metal lathe screw right now. Anyway, thanks for watching. I'll see you later. Oh, there's one thing I forgot to mention. I was trying charging up the supercapacitors, these things down here. I was charging those up to just an experiment, and that's what this meter was earlier connected to. Not sure I got these leads on here. So anyway, I'll show you that in another video sometime. It's not that important right now. As I say, what's important is getting the coils right, because having the coils right makes all the difference, right? Anyway, see you later.